we are going to talk about molecular level thinking. And in chemistry, this is one of the most powerful skills to have, and something that will allow you to be successful as a student in chemistry class. So we're going to take this principle and this skill and apply it to something in the very beginning of either a high school or AP or college level chemistry class. We're going to go ahead and balance a chemical reaction equation. So the particular equation that we're going to balance is the reaction of molecular hydrogen, or H2, and molecular oxygen. Both of these are in the gas phase. And they're going to react in order to produce the molecule water, H2O. All right, so we are going to think about this on the molecular level. Now, this is the really useful skill. The universal law that we're actually applying, or you could say the chemistry principle, is called the law of conservation of mass. And all that says is no matter what process is happening, the total mass at the beginning needs to be equal to the total mass at the end. Now, what this translates to in chemical reactions, when you're balancing equations, is effectively you have to conserve the total number of atoms that you have at the beginning, or the total number of each type of atom at the beginning needs to be equal to the total number of each type of atom at the end. Since each atom isn't really changing identity, they're just swapping who they're associated with or who they're stuck to or bonded to. So in order to understand this a little bit better, we're going to make things simpler. We're going to think about this reaction not on a mole-to-mole basis, which is what teachers mostly talk about. Instead, we're going to talk about this on a molecule-to-molecule basis. So let me go ahead and write us atom legend. This is going to be our atom legend. And let's say a red dot, let's make it a little bit big here, represents a hydrogen atom. And let's say a green dot represents an oxygen atom. Now let's write what we currently have. Remember, this equation that we have written is not balanced. So let's write this in a molecular way. So here, hydrogen, we have one hydrogen, so our one H2 molecule, and that is represented by two hydrogen atoms, and then I'm going to use a black dash to indicate that they're bonded together. Think about that as just sticky glue or a spring holding them together or what have you. Now over here with the oxygen, we know, well, there's a 1 in front, same over here. So we need to write one molecule of oxygen. And so we're going to do the same thing. It's also a diatomic molecule, which means that it has two atoms of the element that we're talking about. So again, we can draw the little black mark to indicate that they're connected together within that molecule. Now, the final product is composed of both hydrogen atoms and an oxygen atom. So let's go ahead and draw the oxygen atom first. And again, we have one of them currently. It's not yet balanced, but let's just draw what we currently have so we can understand how to balance this. So we have an oxygen atom, and we have two hydrogen atoms. Don't worry now if you don't know, if you don't understand why they're connected in the way that they are. You'll get into that later in chemistry. But suffice it to say, an oxygen atom is connected to a hydrogen atom, and it's also connected to another hydrogen atom. So now what we have to do, and there's probably many ways to do this, but one way that I like to do this is let's take a tally of how many atoms of each type of atom we have on either side. So on the left, we'll do something like this. We'll write how many hydrogen atoms and how many oxygen atoms. And similarly on the right, we'll have a hydrogen tally and an oxygen tally. And you might notice this is basically just an accounting problem. It's just very simple, balance your accounting, your checkbook kind of problem. So the question that we ask at this stage is, currently with this equation here, how many atoms of each type of atom do we have? So how many hydrogen atoms do we have? Well, we have one there and we have one there. So currently we have 2. And how many oxygen atoms? Well, we have 1 molecule of oxygen, so we have 1, 2 of oxygen similarly. Now on the right, we have 1 molecule of water, or H2O, which is composed of 1 oxygen and 2 hydrogen. Okay? So now let's talk a little bit more about this law of conservation of mass. This is effectively what we're using to tell us, hey, we don't have enough atoms on the right or the left. So we need to, quote unquote, balance the atoms on both sides. That's what we're doing when we're applying the law of conservation of mass. So we have to ask ourselves, do we have the correct amount of hydrogen atoms on both sides? Well, yes, that's conserved, so that's good. But the problem here is that these are not balanced. So the law of conservation of mass is not, we have not upheld the law of conservation of mass, and therefore this cannot be the appropriate reaction because there's mass that happens to disappear. An oxygen atom just disappears out of nowhere. It doesn't go anywhere, so that's not possible. So we need to find a way to put different coefficients or add different number of molecules of each of these in order to balance both sides of the equation. So we can use integers to multiply each of these molecules. The only thing that we need to remember is we cannot change the identity of the molecules. In other words, we can't just add an oxygen atom here if we want. It's not possible, because then that would be a completely different chemical reaction. So we have to abide by what's above here as the molecule in each of the left side and the right side. So let's see what we can do. Now the general heuristic for when you're balancing an equation and there's things that are unbalanced is to start with the most complex molecule, which just means the one that has the most variety of atoms. And in this case, it's pretty obvious. Water has 2 different types of atoms. On the left, hydrogen and oxygen both have just 1 molecule. So let's go ahead and start with water, H2O. And now from the water's perspective, we want to ask, what number can we put in front of water that will get us closer to balancing the equation? And so at this stage, we can do something like circle that one. We know we need to put a number there. And then we look at our numbers. So we ask ourselves, which one is the one that needs to be balanced, or which multiple ones, and which one is already balanced, just so we know if we do change it, we know we need to change it on the left side as well somehow. So here we look, okay, hydrogen's balanced, but oxygen isn't. We absolutely need to have more water on the right, because we need to up the oxygen. We can't just artificially decrease that, because O2 is always just O2. You can't have just O. So what we need to do is we need to do this. We need to put a 2 in front of water, which then, what that means is we're effectively doubling the number of molecules of that. So we can do a copy paste real quick here. So we're adding another molecule, and then when we do that, the number of hydrogen atoms on the right becomes 4, because we have 4 red dots on the right, and we have 2 total green dots. So the oxygens are balanced, but the problem now is, so these are good, but the problem now is the hydrogens. But if you go over to the left now, you go over to the left side and you can see, well, I have a hydrogen molecule here that only has hydrogen in it. So if I put a 2 in front of that, I will go ahead and balance the hydrogen atoms in the equation, and then both of them are balanced. Okay, so we should add another hydrogen molecule here on the left. And this is the molecular representation of how to balance a chemical reaction, a simple chemical reaction. And notice the stoichiometric coefficients. I'm just going to add a 1. It's just implied. It's like in algebra, like x is the same as 1x. So our stoichiometric ratios are 2 to 1 to 2. Now these ratios, you just think of them in terms of cooking. It's like a recipe. It says, in order to get 2 waters, we need to have 2 hydrogens and 1 oxygen. If we double that recipe and we want 4 waters, then we need to double the ingredients and proportionately double them. So we would need to have 4 hydrogen molecules, 2 oxygen molecules in order to get 4 waters. And similarly on a mole-to-mole basis. Mole just means there's a really, really, really large number. So we have 2 moles of hydrogen for every 1 mole of oxygen that we consume, and we're going to produce 2 moles of water. Okay? So now lastly, we're going to talk about just a simple representation of what this chemical reaction would look like. And this is just a continuation of this molecular level thinking. So let's go ahead and copy paste what we have here. And let's put it down here. And what I want to give you is a visual representation of how you might think about the atoms rearranging. Because Dalton's law, or Dalton's theory of the atom, says one of the principles, or one of the postulates, says that a chemical reaction is just a rearrangement of atoms. And so let's look at this. Here we have in green, that is the oxygen, and in red is each molecule of hydrogen. Now, before the reaction, they're separated. Let's call these are the reactants. We have 2 H2s and 1 O2, just as in this equation up here. And the first step, what's happening on a molecular level, these things are moving closer to each other, and they're going to start, the bond here is going to start to break, which means that the green atoms will start to move away from each other. The red, well, the molecule itself will move closer to the oxygen molecule, similarly here. And so this red atom will start to form an attraction to that one, and this green one, as it moves away from the other green one, will start to move and create an attraction with that one. And at the same time, this H2, as the molecule moves that way, this atom moves a little bit farther away from that one. And this bond here between the H and the H starts to weaken. So the next level, I'm going to draw that representation of that. So here we have one of the atoms of hydrogen, and then we have the atom of oxygen that is getting closer to that atom of hydrogen. And so we're going to start forming a bond there. And then over here, this atom of hydrogen starts to move away. So that's going to also become a dotted line to indicate it's weakening. Over here, this green oxygen atom is also moving away from the one that it was bonded to, and so that is a weakened bond there. And the hydrogen atom over here moved closer, and this one moved a little bit farther away. So this one is starting to form, and this one is weakening between those two. At the next level, what you might have is that these ones form a full bond. These ones form a full bond. This fully breaks, and this fully breaks. So what you have left is you have a hydrogen atom there. You have a hydrogen atom over here that's completely separate. It's just a hydrogen atom. And in the center, you have an oxygen bonded to a hydrogen, which is an OH. This is just an intermediate. It means that it will form into something else very soon. But this is how I want you to think of the reaction. Okay? And that similarly also forms an OH. And that now is bonded. So we go from there to there. And then the next point of attack will be then this hydrogen atom will then react over on this side with this oxygen OH species, and similarly this one will attack that side. And so let's draw that. So here we have your oxygen, and I'm just flipping around this guy. Something like that. And this red hydrogen now starts to form a bond with that guy. And similarly over here, you have your oxygen atom bonded already to your hydrogen atom from the row above. And then the separated hydrogen atom will then start coming closer and bonding with that oxygen side of that. And we have one more step to go, which is just to show that this forms a full bond with the oxygen, and you have an H2O, and this forms a full bond with that oxygen, and that forms an H2O. And so let's draw the final step here. So here you have hydrogen bonded to oxygen, bonded to hydrogen. Remember, the black just represents the sticky glue that glues the atoms together in those particular places. And now I'll just go ahead and copy paste this for the other one, since we have two of them. And that will be the final step. And this doesn't represent reality, but this is the way that I want you to think about when a reaction happens. Things are moving around, bonds are starting to break, and bonds are starting to form. In other words, it's a rearrangement of atoms, just as Dalton's theory of the atom says or tells us what a chemical reaction is. So this represents products. And based on the equation above, the products, you have two H2Os, which is exactly what we have there. So notice you have that, gives us that. All this stuff in between is the steps in order to get to the end. This is something that you'll learn later on, which is called a reaction mechanism. It's sort of a hand wavy one at that, but what I'm trying to get you to do is think on a molecular level and think how you actually get from A to B in a reaction. And so with that, I will end the video.